Profiling part 3, let's talk about some more optimization. We'll talk about some general optimization techniques. First up, function inlining. What does that mean? What that is we're telling the compiler that when I wrote this function, maybe it's a small function, and instead of calling the function, maybe just take the body of the function and paste it right where I've got the call. So like maybe I have a small function that I call often. For example, this dot product. Dot product turns out to just be this small amount of code here. A couple of multiplies. I got 3 multiplies, 2 adds, and a return. Instead of compiling that function and putting it in code somewhere and then branching to that function, instead, why don't you just take those 3 multiplies and those 2 adds and embed them right here where I've called the dot product. Okay, how do we ask the compiler to do that? The first way is, implicit inlining is when you just put it in your header file like this. That's one way. Another one is you can put the keyword inline in front of your function, and then that tells the compiler, you really should consider inlining this one, please. And then, it's weird. Different compilers have different rules, and that's because C++ maintains a very loose standard for inlining. All inlines are actually suggestions to the compiler. There are times when it will not inline your code. Well, first of all, if you do a debug build, there's a flag, and if you check this in your Visual Studio settings, there's a flag that says don't inline. And that's to make it easier for you to debug. That's one of the reasons debug builds run so much slower. We take out optimizations, including inlining. A recursive function cannot be inlined. If you think about it, a recursive function is a function that calls itself. So if it calls itself, how many times would it need to call itself? If each one is a copy-paste of the code, repeat of the code, a recursive function could theoretically go like infinitely, unbounded. So the compiler would have no idea how many times to inline that. A virtual function, as long as you call it virtually, cannot be inlined. So that's because when you call the function, you don't actually know which function you're calling at the time you called it, right? The compiler will put the virtual function table in, and then it will branch to one or the other, whatever. It will branch off to the function that this specific object wants. So that cannot be inlined. And similarly, like a function pointer, which is like I call it a C-style virtual function. Same reason. It won't know at compile time what function that is. And then this last one, which is odd, but the C++ standard says that the compiler can ultimately decide whether or not to inline on its own. And for the most part, you're going to get a lot of mileage just out of that. A modern compiler with optimization settings turned on will inline pretty aggressively and without any of these other hints. You don't really have to give it hints. It will inline your code for you when it's not in the debug mode. So let's take a look at the impact of inlining code. Here's a piece of code in the disassembly that has not been inlined. This is debug compiled, so no inlining. The function call is this one line here, camera C set horizontal dist 300, 300. Okay, so what does that turn into? Ultimately, it turns into this function call. There's the call to the function. So what have we got here? This is another call. Apparently, camera C was a shared pointer. So we have to call the function to extract the actual pointer from the shared pointer. The rest of this stuff, what is this? It's like weird hex number. This stuff is just putting 300 and 300 on the stack so that when you call set horizontal dist, those two arguments will be passed through. So over here, we have the function that's being called. And let's take a look at that. It's this code here. It contains another call. This is a call to a vector2 constructor. Apparently what we do here is we take float min and float max. We see them coming in here. And those go onto the stack. And then the vector2 constructor is called to turn those two floats into a vector2. Then those two values are copied into members of our current camera C structure. So that's what that does. Which leaves us with the question, what is this? That's what this part is. What is this part here above and below? Take a quick look. Tell me if you can figure out what that is. All right, this one is push, 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 push. And this one is pop, 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 and a call check ESP. What is that? That is saving the registers onto the stack. When we call a function in assembly like this, when it returns, we need to be assured that all the registers we were using before the function call have been restored to their original state. So any of these registers that get used by the function here need to be saved on the stack. Then we do our function, and then we need to restore all those registers before we return. That's one of the main reasons why inlining is so important, because all of this stuff gets tacked onto your function no matter how small your function may be. All right, let's see what this looks like inlined. If we inline this function, this is the code. This is it. What is this? This is that 300. There it is again. And what do we do with it? We take this 300 and we copy it into the member offset. Take this 300, copy that into the member offset, and we're done. There are no calls, there's no stack pushes. That is the entire function. And that's because it has been inlined, and the functions that it calls have also been inlined, and most of those ultimately could just be optimized completely away. Here's another optimization that the compiler can use, and in rare cases you may actually do this yourself manually. We used to have to do this manually. Nowadays the compilers are remarkably clever at figuring this out. This is called unrolling the loop. Let's take a look at this memcopy function, which hopefully you're familiar with memcopy by now. It just takes a certain number of bytes. Here's the number of bytes, and then here's the source and the target address. It just copies bytes from one to another. Here it is unoptimized. Unoptimized, we push the size onto the stack, we push the addresses onto the stack, and we call memcopy. All right, pretty straightforward. We have 3 arguments, so we take those arguments, evaluate them. The compiler has evaluated that the size of m per object is 40 hex. So that's cool. And it has evaluated what m per object address is. It's 50 hex bytes beyond what EAX is, which is this pointer. And so it pushed 3 arguments on the stack, call a function, simple as that. All right, what happens if we inline it? We go over here, inline it, we got this. And the question is, where's the loop? There's no call, and that's not too surprising. It inlined it, okay. But what we're doing is we should be looping through how many bytes? We should be looping through 40 hex bytes, copying them from one place to another. But there's no loop here. There's no loop at all. This just says load, copy something from this address to this address, to this register. I'm sorry, right? Move it from this address to this register, and then from that same register to this other address. And then it does that again. From this address to this register, and then from that same register to this other address. So that is doing a copy. It's copying some bytes. Let's ask this question. How many bytes is it copying? This instruction, you can go look it up if you want, but it's a move. I've stressed just to remember that it's a move, and then there's some words, some letters here. It's a move. From to, we always put the destination first. So we're going into a register. Now this is one of those extended SIMD registers. So that's 128 bytes that we're, 128 bits, right? 16 bytes. So we're going to take 16 bytes from this address and copy it into this register. And then from the register out to a different address. So those two instructions, this one and this one, copied 16 bytes from one spot to another. And then here we go again. We're going to do that again, copy 16 more bytes, 16 more bytes, 16 more bytes. How many bytes did we copy? 64 bytes. How many bytes were we supposed to copy? 40 hex. What is 40 hex? That's right, this is 40 hex bytes copied. You can also see that here when you see how the memory address progresses at each step. It goes from EBX plus 50 to EBX plus 60 plus 70 plus 80. It's going by 10 hex each step. That's 16 bytes each step. And then over here, it's going ECX plus 10 hex, 20 hex, 30 hex. So it's also going, the source and the destination are both going up by 16 bytes at a time. This is what we call unrolling the loop. It's taken what would have been written as a loop for I equals 0 to 16, or for I was 0 to 64, copy the byte, copy the byte, copy the byte. And instead of doing it in a loop, it said, well, actually, I know how many times it needs to do it. And so I can just drop the loop counter, I can drop the branch, I can drop the compare, and just do it 4 times, right? First of all, kudos to the compiler for realizing it can do it 16 bytes at a time instead of having to do it a byte at a time or 4 bytes at a time. It realized it can copy 16 bytes at a time, and then it also realized that just doing that 4 times with these 8 instructions will be faster than the loop with the loop counter. All right. Another trick we have, now and this one is not a compiler trick, this is something you'd write into the software. It's something called a lazy update. How does that work? Let's look at an example. Let's say we have this piece of code where you have a sprite and you set the scale, you set the position, you set the rotation. That's a fairly common access pattern. Fairly common, you'd want to set the position, set the rotation, maybe update the position a couple of times. Maybe it's like a collision routine and then you bump into something, so you update the position, yada, yada, yada. In our engine, we've stored the position and the scale and the rotation in a matrix. So every time you called one of those functions, you'd have to update the matrix. That could be kind of expensive, especially if we have this pattern where we keep updating it over and over, like so, like you set the position, set the rotation. That would be at least, those 2 matrix updates. Where if we realize that's what we were doing, we could be smarter about it and just wait until you have the position and the rotation ready to go and create the matrix the one time. The flip side of that access pattern is somebody somewhere is going to ask for that matrix. Now, if they ask for that matrix and we calculate it then what if they ask for it multiple times? What if somebody asks for the matrix and then somebody else asks for the matrix? So now we're doing extra computes on that end. So enter the lazy update. With the lazy update, we defer the calculation, the expensive calculation, until the first time somebody asks. Here's how it works. So let's take a look at that set scale function. For the set scale function, we would just store the scale in a member variable, right? We would copy that scale into the member variable and we would mark the matrix as dirty. We'd say that matrix is out of date, right? And we'd have similar functions for position and rotation where we copy the input value into a member variable and mark the matrix dirty. But we do not update the matrix. until somebody calls get world transform. Now we ask, is the matrix dirty? If the matrix is dirty, then we update that matrix, we update the transform, and we mark it as clean. And then return it. So the next time somebody says, hey, give me that world matrix, you say, is it dirty? No, it's not dirty. There you go. Have the ready to go. And if you have, like, gameplay engineers who have been very willy-nilly about this, setting multiple terms multiple times during the update frame, and then maybe multiple other services have called, have relied on getting that matrix back, then this can be an optimization. Okay, because now we only call the compute world transform, which is really the expensive part. We only call it once when it's needed, but we haven't really had to drill in to figure out when it's needed. It's sort of automatically figuring it out for us. However, I will say, always profile it to make sure this is a win, because we have inserted an if. We've inserted an if on every single call to get world transform. Real true story here. I actually found an optimization on a team that was using lazy update in their case, because there was one call to get world transform for every object per frame. It turned out there was only one call to get world transform per frame, so we didn't need the if. Just dump the if and just compute the world transform. So here's one last trick I had to share with you, and this is frankly my greatest one. This is the best thing I can let you in on when it comes to optimization. Here's the trick to optimizing. Say you've got some slow process, like maybe enemy pathfinding. That tends to be pretty slow, all that A star, right? Well, let me ask you this. Do you need to run that on every single frame for every single enemy? No, right? I mean, the path doesn't change that often. Even if a door closes, how long could we wait before updating the enemy and have nobody notice? The door closes and the enemy doesn't notice for a whole second. Let's say a whole second. Like a second, is that a long period of time? Well, if we're running 30 frames per second, that's 30 frames. 30 updates have gone by and nobody told this enemy that the door was closed. So maybe for a whole second he still started walking towards the door, and then he suddenly realizes the door's closed and he turns away. Frankly, that could look more realistic, right? He's got a little bit of a delayed reaction. Okay, that's an example. What could we do? Well, let's say we'll update them every 10th frame, so it isn't quite that long a gap. Every 10th frame, maybe, we'll do these expensive updates. So your first thought might be, okay, I'll only do pathfinding on every 10th frame. Now your average speed will go up because 9 out of 10 frames you're not doing any of this pathfinding. But then on that 10th frame, you'll get a really slow frame. So you get fast frame, fast frame, fast frame, slow frame. Fast frame, fast frame, fast frame, slow frame. And so the game won't be smooth still. But there's another trick. Recognizing that in this case, we have a lot of enemies that have these pathfinding requests. What we can do is spread them up so that let's say we have 100 enemies that all need to have their paths updated. Let's do 10 of them each frame in a rotating queue. We'll just take the 100 enemies and we'll spread them out across 10 categories, and each frame will handle one group. So if we have 100 enemies, we'll have 10 in the first frame, 10 in the second frame, 10 in the third frame. And then when we're done with that last group, we cycle back to the first group again and update them. So it may take as long as 10 frames to get through this whole list, but that's still a third of a second. And probably no one's going to notice. So I've used this in a multitude of different situations. You can get huge optimizations with very little code. The beauty of this one is I'm not worrying about like low-level difficult code like cache coherence. I'm not worrying about that. I'm not worrying about converting things into SIMD or trying to create compute shaders for things. All I'm doing is saying, hey, take this big group, split them into 10 small groups, and we're going to handle one group per frame. And we just go around in a circle. And I get a 10 times speed up by just doing that. Now, if I was to convert this to SIMD code, maybe I could get a 2x speed up, right? That'd be cool. That'd be a good speed up. But I got a 10 times speed up just by splitting things into groups. This is huge. So that's it for profiling. Don't forget there's an at-home assignment on Blackboard waiting for you, and that's due before we meet again for the next class. And during the next class, we will begin our profiling lab, and I'll see you then.